All right. All right. So today we're gonna continue with non-abelian gauge theories, and in particular, we're gonna discuss two important aspects. The first one is asymptotic freedom, which was the reason why this theory was considered useful, in particular for QCD, describing nuclear physics, and then a theoretical tool called Rst Symmetry, which we will use in the next lecture to derive some relations between correlators and between various renormalizations. All right, so let's first start with asymptotic freedom. So, as I said, this is a very important concept, and so important that it gained a Nobel Prize for David Gross, Franz Wilczek, and David Politzer in 2004. And asymptotic freedom means really the fact that at high energies the coupling goes to zero. But of course, since we cannot do this non-perturbatively, I mean, we cannot do it. Well, we cannot calculate all loops, but since we are interested in the really high energy behavior, we assume that this is correct only by doing the one loop calculation. So we've already done the one loop calculation, and in particular we have calculated the one loop renormalization of the coupling. We found that the bare coupling is related with a renormalized coupling by this ratio Z1 over Z3 to the power 3/2. And of course, this was in 4 dimensions, and really, if we are careful with dimensions, this was not G, this was really G tilde, so it's actually G mu to the epsilon over 2 times this factor. And we've calculated at one loop this Z1 and Z3. So this is the classical part, 1, and then the one loop part proportional with G squared over 16 pi squared. And there's a piece coming from the gluons that's proportional to the quadratic Casimir of the group that is in the adjoint, C2G. And it's positive since, well, I mean, you can choose any alpha, but at least if I choose alpha equal to 1, this will be positive. Whereas if I add the contribution of the fermions proportional to TF, which is the trace TATB in the representation of the fermions, this contribution then is negative to both. It's with -4 over 3. And then we have the infinite part, 2 over epsilon. All right, so then calculating the renormalization at one loop, that is to say, I write this Z1 divided by Z3 to the 3 over 2, but remember I expand in G squared, even though 2 over epsilon is actually infinite. that I expand in G squared. So it's G mu to the epsilon over 2 times 1 plus, and then this part minus 3/2 times this part. Okay. So the contribution with C to G is this minus 3/2 times this. The contribution to 4/3 is minus 4/3 T fermion, 1 minus 3/2. And all in all, then we see that in fact the contribution 3/4 plus alpha. So this, at least at one loop, is independent of the gauge. Well, we can prove, in fact, that's independent of the gauge, but for the moment, we've just shown that it's independent of the gauge parameter alpha in the Lorentz gauge. So, as I said, there's a contribution in here. Oh, and there's a overall minus. And so there's contribution with a minus coming from the gluons, proportionals with C to G. And there's a contribution from the fermions, which was with a plus that is in this proportional with this TF. All right. Then, in order to calculate the beta function, we take mu times the derivative with respect to mu being the dimensional transportation parameter, the arbitrary quantum scale introduced by renormalization. So since this G0 is the bare parameter, it's not renormalized, it's an infinite parameter in the Lagrangian, then this is independent of mu. So d mu of G0 must be equal to 0. But on the other hand, G does depend on mu. And so there's this contribution mu dd mu G times well, oops. Where was I? Yeah. So there's this contribution with dd mu G that's proportional to the same mu over to the epsilon over 2 times this whole thing, 1 minus G squared over 16 pi squared times this. All right. Then I act also on mu itself to the epsilon over 2. So then I get this epsilon over 2 mu epsilon over 2 times G times this. So times G minus G cubed over 16 pi squared times this. All right. And of course, since this is only normalized up to loop order, one loop order, and in here I have terms of order at most G cubed. There are further terms that will start at G to the 5. All right, but then you remember that this mu dd mu G is what we called the beta function, and if mu is non-zero, if epsilon is non-zero, this is beta of mu and epsilon, right? and so it's just the ratio. So it's minus this divided by this. All right. So it's written here. All right. So so let's note that the denominator is infinite, in the sense that, well, the term proportional to g squared is infinite. It's proportional to over epsilon. But in here, in the numerator, I have a term proportional to epsilon. So, like, once again, I must expand in g squared, even though the denominator in principle is infinite, is proportional to 1 over epsilon. I expand this in g squared, so that means it's the numerator times 1 plus this g squared, 3g squared over 16 pi squared, 2 over epsilon times this contribution. And of course, if I multiply with minus epsilon over 2, I get, well, first minus epsilon over 2g, but then this times this. So then 2 over epsilon cancels with epsilon over 2, and I get minus 3g squared minus 3g squared over 16 pi squared times this contribution. But then in the numerator, I had plus 1 times the same thing, g cubed over 16 pi squared times this contribution. So overall, the contribution is minus 3 from here, plus 1. It's minus 2, g cubed over 16 pi squared times this contribution. And note that that in principle, this could be so I expanded I consider this g squared as infinitesimal, right? Small, but actually 2 over epsilon is divergent. But moreover, I wrote 1 over 1 minus stuff as approximately 1 plus stuff. But we know that this is called x, 1 over 1 minus x is 1 plus x minus x, plus x squared plus x cubed plus blah, 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 right? So if I would actually continue, if I would continue to expand this in epsilon, I would get a term with 1 over epsilon squared, right? And then I would get a contribution. So epsilon over 2 times 1 over epsilon 2 over epsilon squared, I would get a contribution that would be divergent, but it will be proportional to g cubed, right? But as you see, in fact, there's a further g cubed contribution that I've neglected because it's 2 loop. So this expression, expanding it, formally becomes divergent in epsilon, but only because I've not included the 2 loop contribution. If I would include the 2 loop contribution, the second, or the g cube contribution, would also be finite in epsilon. All right. And then, as usual, the beta function, beta of mu is obtained, beta of g, or beta of g rather, is obtained when I put epsilon to 0, so I cross this term, and then obtain this first contribution proportional to g cubed. All right, so beta of g start with this g cubed contribution times something that I'll call here beta 1, and then I would have further contributions from 2 loop, 3 loop, 4 loop, and so on. And the expansion, as you see, is in g squared over 16 pi squared. So the next term will be proportional to g cubed, and then with g seventh. So by definition, I define it like this. There's an off-null g squared, and then the first coefficient is called beta 1, the second beta 3, the third beta 5. All right, so this is 1 loop, 2 loop, 3 loop. But at 1 loop, we just get this. So it's minus 2 over 16 pi squared times this contribution, 11 over 6 C2 of G minus 2 over 3 TF. All right. So we've seen that beta 1 is independent of alpha, even though in this Z1 and Z3 there was a contribution with alpha. And moreover, I said that you can check that in fact it is gauge independent. So even outside the Lorentz gauge, here it's we've just shown that it's independent of the alpha parameter of the Lorentz gauge, but in principle it's also independent of whatever gauge we do. And the same is true for the 2 loop contribution for beta 3. This is also gauge independent, that is universal. They're both non-zero. And moreover, they're both independent of the renormalization scheme. So these beta 1 and beta 3 are truly universal. But the other contributions are actually not. In principle, even in here, there was, it's a kind of miracle, or not miracle, but there's a cancellation that could have not happened between the terms with alpha. So in principle, the lower orders, so starting at 3 loop, and they are not universal. And they also depend on the renormalization scheme. But with respect to our goal, asymptotic freedom, we note that the contribution of the gluons, so the term proportional with C2G, is negative, so it's minus this number times C2G, whereas the contribution for the fermions is positive. It's minus times minus, so plus TF, which is always positive, and some number. Okay, and the same would be true for any other kind of fields. Here we've shown just for fermions, but you can calculate 1 loop contribution for scalars, for 3/2 fields, gravitinos, and so on. But the only positive contribution that you find is for non-abelian gauge fields. So beta 1 being negative is only possible if we have non-abelian gauge fields. So why do we say non-abelian? Because we've calculated the QED contribution at 1 loop. beta function, and we've seen that it's positive if we consider the electrons. And the point is that C2G is 0 for the abelian group for U1, because really one considers that the TA, the generator, in the adjoint representation for U1 is equal to 0. So then, of course, C2G is also equal to 0, since C2G is TA squared, the sum over the TA squared. Whereas TA is equal to 1 for U1 in the fundamental representation where the electrons are. So TF is equal to 1 for QED. So beta 1 for QED, this is 0, this is 1. Then we get plus 4 over 3 times 16 pi squared, so plus 1 over 12 pi squared. All right. I've calculated the beta function at one loop. Now, really, the beta function, the point of the beta function is that it's the variation with respect to the arbitrary mu parameter. But you remember that from this we were able to derive a dependence on the physical mass scale, or G squared of T, if you want. But to simplify, we just integrate with respect to mu. And then this can be translated into G squared of T in the same way. But just integrating this with respect to mu. So I have mu dd mu of G is beta 1 times G cubed. So I multiply with 2G. Then here I get 2G4, and here I get the derivative of G squared. Right? So that means that G squared so derivative with respect to log mu is 2. So then if I put 2 here, I get d log mu squared. So dg d log mu squared is beta 1 G squared squared. So the solution of that is that G squared of mu is G squared of mu 0 divided by 1 minus beta 1 G squared of mu 0 times log mu squared over some scale mu 0 squared. Okay. So the point is then that since beta 1 is negative, then in here I have 1 plus, so beta 1 so if beta 1 is negative, like for QCD, as we'll see, then I have G squared is proportional to 1 over 1 plus something times log mu squared. So that decreases logarithmically with respect to the scale mu squared. So that's kind of what I tried to show here, that G squared goes to 0 at large mu. All right, so what does that mean? So that G squared increases at small mu, and decreases at large mu. And mu is an arbitrary quantum scale, but as we've shown in when talking about the RG flow, the renormalization group equation, I can translate this into a g squared of t, and t is basically the ratio of momentum squared divided by some fixed momentum squared, all physical. All right, so that means we have these two properties. We have so-called infrared slavery, meaning g squared when mu goes to 0 is infinite. So at small energies in the IR, or in other words, at large distances, we have very strong coupling. So that leads to confinement, right? So in QCD, we know that we cannot separate the quarks and the gluons. The quarks and the gluons tend to be are bound together. When you try to break them apart, you cannot. Their binding grows faster and faster, right? So that's the point described here, and in terms of IR slavery, that the coupling at large distances, when you try to break apart quarks and the gluons, goes to infinity and makes it impossible for you to break them apart. And the other property is the one that we've advertised, asymptotic freedom, meaning that when mu goes to infinity at large energy scales, g squared goes to 0. So the theory is free in the UV, is asymptotically free. So that is why we can collide in QCD. We can collide particles at high energy, and we only need to calculate a few loops, and you agree with experiment very nicely because the coupling is very small. All right. Now let's actually calculate for QCD. First, let's be a bit more general. So let's talk about the group SUN with arbitrary n. The quadratic Casimir of the group SUN is n. You can calculate that. I'll not do it, but and then as also I've mentioned before, the TF, which is the usual convention. If you fix trace TA TB to be delta AB in the joint representation, then in the fundamental representation, when you have TF, we have 1/2 delta AB. So TF is 1/2. But in QCD, we will consider, so in this case, a more generalized QCD. So group SUN, gauge group SUN, we consider NF flavors or species of fermions. So NF fermions in the fundamental representation. So the total TF is the 1/2 for each fermion. But then when I sum over fermions, I get 1/2 NF, right? So the formula was so -1/16 pi squared, 11/3 C2G, -4/3 TF. So now I have indeed minus 1 over 16 pi squared, 11 over 3 C2G is n, or the number of colors, NC, minus 4/3 times 1/2 times NF, that is minus 2/3 NF for the fermions. Okay, so this is SUN with, so NC colors and NF flavors. In the case of QCD, we have NC equal 3 colors, and NF equals 6. As 6 flavors, which are up, down, charm, strange, top, and bottom quarks. So then for QCD, replacing it in here, the 3 cancels, so I got 11 minus, and F is equal to 6. So 6 over 3 is 2, so minus 4. 11 minus 4 is 7. So beta 1 for QCD is minus 7 over 16 pi squared. It's negative as advertised, which means that QCD is asymptotically free. And it's also exhibits IR slavery leading to confinement. Now these statements, this calculation beta of QCD being minus 7 over 16 pi squared, and the corresponding idea of asymptotic freedom and IR slavery were in the papers of Gross, Wilczek, and Politzer. I don't remember exactly when the papers were and how they were distributed, but this important statement is the reason they got the Nobel Prize for. All right. So this was about asymptotic freedom. Now let's talk about BRST symmetry. This is something that didn't receive Nobel Prize, but only because this is sort of a mathematical tool that has not led to any experimental obvious experimental implications. And as you know, Nobel Prize needs to have some experimental implications. But in my mind, it's as important. It's certainly one of the most important modern tools in gauge theory and in string theory, and perhaps in other places as well. So so what is this BRST symmetry? So we've worked with gauge theories which had some gauge invariance, but we've seen that in order to define well the quantum theory from the path integral, we had to gauge fix. We had to fix a gauge. And that means that we don't have any more gauge invariance, meaning local symmetry under the group. But that not having the gauge symmetry means that I cannot obtain word identities. So I cannot obtain useful relations for the quantum theory. But we need something to replace it, and there's a global symmetry, that's BRST symmetry, and that's a residual gauge invariance, a remnant of gauge invariance after fixing the gauge. BRST stands for the people who found it. In 2 papers, one of Becky Rouet Estora, Frenchman. Becky, I guess, is Italian, but the point is, this was in the time of the Cold War, so this was in the West, whereas in the East, independently, there was a paper by Tutin, and since it was kind of very difficult to communicate between the two, people were not aware of it. So in some places, some people still call it Rst symmetry, since they were only aware of the paper of Becky Rouet and Stora. But it's really Rst because they were independently found on different sides of the wall. All right, so in the formulas of Rst symmetry, we'll deal with gauge fixing and ghost action, and for the ghost action, we'll use the terms B and C for the ghosts that come in the so for the complex and complex conjugate, complex C and complex conjugate B. Since this is what is used in the Rst literature. So the Lagrangian, the quantum Lagrangian, depends on the gauge field A and the ghosts B and C. And in Euclidean space, we have the gauge kinetic term, f squared over 4, the gauge fixed term, d mu a mu squared over 2 alpha, and the ghost term. So before I partially integrated del mu inside, then I had minus b del mu d mu c, but now I keep it on b, so I have plus d mu ba, plus del mu ba d mu ab cb. I remind you that the ghosts B and C are anti-commuting variables, and if I choose C to be real, in order for the action to be real, then B must be imaginary. So anti-Hermitian. That's another way of saying C Hermitian, B anti-Hermitian. But with respect to the dimension, the only thing that we know, so we know that the action must have dimension 0. So in 4 dimensions, the Lagrangian has to have dimension 4. We have 2 dimensions from the 2 derivatives. So the only thing we know is that the dimension of B plus the dimension of C is 2. But a priori, as I've emphasized before, B and C are independent fields. I mean, we had formally written at some point integral over eta bar and integral over eta. But even in that point of view, I emphasize that they're independent integration. So that's why I wrote it B and C. So we don't need to choose the dimension of B equal with the dimension of C equal to 1. That's one choice, but any other choice is possible. In particular, in string theory, people usually use other choice, a choice where dimension of B and C are not equal. The only constraint is that the sum of the 2 must be equal to 2. All right, so with these preliminaries over, let's talk about BRST. So BRST is a residual gauge symmetry. So we have to show first the gauge transformation. Well, gauge transformation acts on a mu, and the result is the covariant derivative d mu acting on an arbitrary lambda of x, parameter lambda of x. So that's del mu of lambda a of x plus g f a b c a mu b lambda c of x. So there's this arbitrary parameter lambda a of x. A residual symmetry means that residual gauge symmetry means that we have some constraint on the dependence on x of the parameter. I told you that BRST is actually a global, it's not just a residual gauge symmetry, but it's actually a global symmetry. So lambda a of x must have a well-defined dependence on x. And actually, the dependence of x is given by the C field. That means that so lambda a of x is replaced with CA of x times an arbitrary lambda, which is now constant, so giving a global symmetry. All right, so that's my starting point. So the variation on the BRC symmetry of A mu A is d mu of lambda, where lambda is CA of x times lambda. It's useful to, in order to analyze BRST symmetry, to talk also about something that we'll call ghost number, by defining the ghost number of C to be +1 and the ghost number of B to be -1. This is since initially I had this notation with C was eta and B was eta bar. So from that point of view, so that relation, writing eta and eta bar, was meant to, in this sense, that the action is supposed to have ghost number 0, which means if the ghost number of C is +1, then the ghost number of B is -1. All right. Since lambda, the arbitrary lambda a of x parameter, doesn't have ghost number, its ghost number is 0. But then this is equal to CA times the global lambda. That means that the ghost number of global lambda is -1. Then further, lambda a of x was commuting object, was a parameter, normal commuting parameter, but is equal to an anti-commuting field CA of x times global lambda. Global lambda, therefore, must be also anti-commuting. Now, since this CA of x global lambda is a special type of lambda A, and since the classical Lagrangian was invariant under any lambda A of x, that means trivially that the BRST transformation of the classical action is 0. And moreover, as I said, the BRST variation of A mu A is d mu C A lambda. All right, so that's a starting point. Now we can extend this actually further. So I said here classical Lagrangian, but I only talked. I only wrote before the classical gauge Lagrangian, but in principle I can also couple the gauge field to matter, and then I also have a gauge invariant theory, gauge invariant Lagrangian. So that means that I can also restrict the gauge transformation of some field, which in general is equal to minus G times the generator TA in the representation of I, so with ij phi j times the arbitrary lambda a of x. I can restrict this and obtain its BRST transformation by just replacing lambda a of x with Ca of Ca times lambda. Okay, so I have the BRST transformation of A mu and of whatever matter field. But now I have to find the BRST transformation of B and C. So the extra terms are a term with the gauge fixing term with d mu a mu squared over 2 alpha, and then this ghost action minus BA del mu d mu Ca. And d mu a mu squared, when I vary it, I get a term with a mu and a term with the variation times something with the variation of a mu. And the variation of a mu is this. So it has only the ghost C, but not the anti-ghost C, but not the ghost. The ghost C, but not the anti-ghost B. So that means that in order to have invariance of the quantum action, since so this is invariant, and then this must be invariant, this sum must be invariant, but this, as I said, there is something like a mu times the variation, which is proportional with C. So therefore the variation of this thing does not have a B in it. But then in here I have a term where I have B, so minus B, where I wrote it, minus B del mu times the variation of covariant derivative of C. So this term cannot be cancelled by some other variation. So that means it must vanish by itself. So that means that the variation of covariant derivative d mu on C must be 0. But this is equal to well, the variation of del mu C, I can pull out del mu, plus the variation of this term with a mu times C, so in which I can vary first a mu. So this is G FABC, the variation of, sorry, the variation of A times C. And finally, G of ABC A times the variation of C. And now I can combine this term and this term and obtain a covariant derivative. So you see, this is d mu C, but on it I act with del mu plus G f A B C A mu B. So that's the covariant derivative. Right? The covariant derivative, this times this. So the first plus third is the variation of del sorry, the d mu of delta Ca. And then I have this term where I could actually pull out the covariant derivative from this whole thing. Now I have a covariant derivative on C, that lambda times another C. So this is something like del C times C, but that's something like del C squared. So for the normal derivative, del mu, that is certainly true. But I must show that is also true for the part that has gauge field. So in order to show that the part that has gauge field also acts correctly, I must show that so the part with a mu in this one, which would be this, is equal to part with a mu in this one, which is this and this. So in here I have an f outside, and then inside the covariant derivative I have another f times a. So I have two f's, and then outside I have the a mu, and then the two c's and lambda. So what I have is a relation like this: 1/2 a product of two f's that are summed over summed like this over Q, and then summed like this over Q as well. But moreover, down here I have PBC, and here I have CPB. All right. Now, how do I find this relation? So you see, the first observation is that I have multiplication here with CB lambda CC, but I remember that CB and that C and lambda are anti-commuting objects. So actually, interchanging the indices B and C gives me a minus sign. So basically, multiplying by this thing, since otherwise the fields A and C are arbitrary, it only means that I have to anti-symmetrize in B and C. Now this F here is already anti-symmetrized, but here anti-symmetrizing over B and C is non-trivial. So really what I must do is I multiply this bracket by a factor of 2, then I get a factor F here. And here anti-symmetrizing, 2 times the anti-symmetrizing, means there are 2 factors, one like this and another one with B and C interchanged. But then I further found that here in this sum, so Q here up is fine, but here Q is on the second position, whereas here is on the first position. But F is anti-symmetrized in these indices, so I can switch this P and Q here and get a minus sign. Then what I have in the end is the sum of 3 terms with F times F, with Q summed over the in this way. So last here and first here. And then the lower indices are in the cyclic position. So PBC, BCP, and CPB. All right. So this equation then, this is 0 because of the Jacobi identity. I think we talked about this before. So basically the Jacobi identity is an identity, something like 0 equals 0. That comes when you write the double commutator of the generators of the algebra. So let's say TA commuted with the commutator of TB, TC, and then plus cyclic in ABC, plus 2 cyclic terms in ABC. This is identically 0. You just expand the double commutators and you cancel various terms. So this is exactly equal to 0 times 0. However, you could also do it by writing the first commutator inside as structure constant F times another commutator T. But this is commutated with the first commutator, so this there's still another commutator giving still another structure constant F times a generator. So basically it amounts to this, the cyclic sum of cyclic sum of product of structure constants summed like this. All right. So because of this equation that comes from the Jacobi identity, we find that I can rewrite this term like this. So then finally, to obtain the variation of C, I've seen that the variation of covariant derivative on C must be equal to 0. And I rewrote this as covariant derivative of variation of C plus covariant derivative of 1/2 G FABC C lambda C. All right. So in this, I can first put A mu equal to 0, and then covariant derivative here and covariant derivative here turns into normal derivative and normal derivative, which I can just peel off. So I can just write that the variation of C is equal to minus G FABC CB lambda CC. Right? So this is the solution, at least at A mu equal to 0. But then I can put in back A mu and check. So check that if I put this variation equal to this, then the equation is still satisfied. So so indeed we have found the variation of C. Good. So now what do we have? Well, I've shown that the variation of the ghost Lagrangian is equal to so it's variation of B times d mu del mu d mu C plus B del mu d variation of d mu C, which was however 0. So it's equal to just the variation of B times del mu d mu C. But this must now cancel with the variation of the gauge fixed term, which is, so it was 1 over 2 alpha del squared del A squared. But if I vary, I get 1 over alpha del A times del mu times the variation of A. And the variation of A is d mu C lambda. Okay, so I get this. So now I guess I have to cancel this against this. But I note that I note that this is the same as this. So that means that the variation of B must be equal to minus 1 over alpha d rho a rho times lambda. All right, so now we finally found that the quantum action is BRST invariant under this variation. Variation of A is covariant derivative on C times global parameter lambda. The variation on C is 1/2 G FABC CBCC times global lambda. And the variation of B is minus 1 over lambda d mu A mu A times lambda. I can generalize this a little bit more, since I note that this is the gauge condition. So the generation of the Lorentz gauge. So this I replace, or I call, in the case of Lorentz gauge, I call this FA. Right? So then the gauge fixed term, I write it as FA FB, 1/2 FA FB times gamma AB. And gamma AB, I defined to be delta AB over alpha. But then I also saw that in this more general case, the ghost action is actually minus B times the variation of the gauge fixing function, Fa, times covariant derivative on C. And now then I can I can note that this, so the ghost action was minus B times well, the variation, yeah, this thing, sorry. So minus B times the variation of the gauge fixing function with respect to A times the covariant derivative on C. But now I can rewrite this as the BRST variation of Fa, because you see, in general, I can replace, as I said, the variation BRST variation with minus 1 over alpha Fa times lambda. So if I divide this from the right by lambda, that is, I remove lambda from the right. Remember, lambda is anti-commuting. And in principle, Fa could be as well. I mean, could contain something anti-commuting. So removing lambda from the right, I get this Fa, right? So so its variation then, it's the variation is d mu times the variation of a mu, which is covariant derivative on C. All right. So this works out in the certainly in the Lorentz gauge case, and in the general case, if I do a BRST variation of F, then that amounts to first. So the gauge will depend on A, so I vary with respect to A, and then I vary BRST vary A, which will give me this. Okay, and removing lambda from the right, because otherwise lambda would be here. Okay. And then, as I also said, the variation on B is equal to B times lambda, is equal to the gauge fixing function F times lambda, and then I have 1 over alpha here times delta AB. So that's this metric gamma AB. So I write it as minus gamma AB FB lambda. Okay, I can also check this more precisely using using this gauge fixing term and this gauge term, this gauge term. So if I vary this gauge fixing term, I get gamma IB gauge fixing function times the variation of the gauge fixing function. And then if I vary this already has a variation on on FA, and then I only need to vary the BA, which gives again gamma FB. So this second term, the variation of the ghost term, of the ghost action, equals to this, which is also quadratic in F's. So these two terms cancel. Oh, sorry. This is this is supposed to be plus. All right. So I've seen that I can write that I can find the BRST transformation, and for the Lorentz gauge, and I can generalize it to any gauge. Now, we can show that the BRST charge squares to 0. What does that mean? Well, the BRST is a global symmetry, and with it we can associate a generator or charge that, so if the infinitesimal transformation is with a parameter lambda, then variation means by definition is QB acting on the corresponding field times lambda, and then the final transformation is with exponent of QB times lambda, in the same way as the final transformation of global symmetry with e to the generator TA times parameter alpha A. So QB must be so-called nilpotent, that is, it must square to 0. That means that varying twice any field gives 0. So first, let's see it on A. If I vary first the gauge field, I guess I get the d mu c lambda. Then I vary one more, this d mu c lambda. But we've seen already that the variation of d mu c is equal to 0. So that means that the second variation, BRC variation of the field A, is equal to 0. Now, acting on C, the variation, BRC variation of C, we found it to be 1/2 G FABC CB CC lambda. And then let's vary it once more. So let's vary this product. So FABC, CBCC. C's are anti-commuting, and so is F. So this is 2 times FABC, CB times variation of C. But variation of C itself was this. So substituting, we get this. So this is FABC, FCD times CBCDCE. But CBCDCE is totally antisymmetric. I mean, is at least cyclically antisymmetric because of the anti-commuting nature of the C's. But we've already seen that so this is summed over last index here C and first index here C. But we've already seen that the antisymmetric sum of the product of two such F's is equal to 0 from the Jacobi identity. That was this identity. So that is equal to 0. So the second variation of C is also equal to 0. However, for the anti-ghost B, the second variation is not quite 0. Varying it once, you get d mu a mu lambda minus 1 over alpha d mu a mu lambda. But if I vary now a inside this variation, we know that this is covariant derivative C times lambda, a different lambda. So now the result is minus 1 over alpha del mu d mu C A times the two lambdas. That's non-zero, but non-zero off shell. On shell, it is 0 because the equation of motion of B, the anti-ghost only appears in the ghost action, which is BA minus BA del mu d mu C. And so when varying with respect to F, I get that del mu d mu C is equal to 0. So that means that the variation, the second variation of the anti-ghost is 0 on shell only. In other words, QB squared, the action on any field, the second action on any field, is only 0 on shell. This is a familiar situation for symmetries. In particular, for in supersymmetry, this is something very common. In supersymmetry, one also finds that the algebra of charges or generators closes only on shell. So always, in order to make it close off shell, so here the algebra, so to speak, quote unquote algebra, is just q squared equal to 0, or another way of saying it is that the anti-commutator of QB is equal to 0, since QB is an anti-commuting object. So we know how to make this close off shell. We must first go to a first order formulation by introducing some auxiliary field. and the auxiliary field must be such that that must equal the field equation that we want to vanish. So in our case, what we found non-zero was this term. So the second variation meant the first variation of d mu a mu lambda. And this thing was the gauge fixing term. So what that means? That means that we must find the first order formulation for the gauge fixing action for d mu a mu squared over 2 alpha. We'll find it introducing an auxiliary field that's called the Nakanishi-Lautrup field dA. So first order formulation means introducing this auxiliary field. So the gauge fixing action is equal to 1 over 2 alpha d mu a mu squared. But I want to write it in a first order form by introducing this auxiliary term. So I write it like this: minus alpha over 2 dA squared minus dA times d rho a rho a. You see that if I solve for the auxiliary field dA, its equation of motion, so when I vary here, I get dA, and here I just erase j, so the equation of motion is dA is equal to minus 1 over alpha d rho a rho a. And when I substitute back here, I find d rho a rho a squared over alpha minus 1/2 times the same thing, so 1 over 2 alpha d rho a rho a squared, which is our gauge fixing action. So indeed, this is a first order form for the gauge fixing action. Therefore, now I remember that the variation of BA was equal to this minus 1 over alpha d mu a mu a times lambda. But this is now equal to dA. So I write it as the variation of BA being equal to dA times lambda. And on the other hand, I put the variation of dA to be equal to 0. Now, explicitly we find that the second variation of BA is equal to 0 because the first variation is dA, and the second variation is the variation of dA, which is equal to 0. So now we have explicitly that QB squared is equal to 0. That means which means that the second variation on any field in the theory is equal to 0. Now, I haven't, so I rewrote the variation of BA like this, and the variation of D like this equal to 0. So this is our assumed BRST variation, but the gauge fixing term was removed by this first order form. So let's check that we get correctly 0 for the variation of the quantum action. The variation of the gauge fixing, the Gauss term, is as usual the variation of BA times d mu CA, sorry, with minus in front. And then the variation of this term is 0, since the variation of B is equal to 0. And then the variation of this term is the variation of dA is 0. And then the variation of this is d mu del mu C. So we get dA variation of d mu a mu plus variation of B times d mu C. So indeed, the action is invariant. Now we obtain that QB squared is indeed off shell equal to 0. One more observation that is useful is that since the variation of B, which is the variation of B acts as QB lambda, and since the Gauss number of lambda is -1, and since the variation must have Gauss number 0, that means that the Gauss number of QB is +1. But another observation, which is more important, is that the Rst transformation rules are now purely kinematical. They do not depend on the form of the action, right? So the variation of A is covariant derivative on C lambda. Whatever the action is, the covariant derivative is always defined kinematically independent of the action. Variation of C is also independent of the action. FABC is from the gauge group, and CBCC again does not have anything to do with the action. Variation of B is D. Variation of D is 0. So all of these things do not depend on the action, whereas before things did depend on the action, because we had in here the variation of B proportional to d mu mu and the Lorentz gauge, or more generally, the gauge fixing function Fa, which is part of the dynamics of the theory. So this formulation is very nice. We have seen that now QB squared is 0 off shell, and QB acts kinematically. Now, one more observation is that the Gauss term can be rewritten as minus B times the variation of the gauge fixing function divided by lambda. Right, so that I've already written in here. But now also the gauge fixing term, which was gamma AB dA dB minus dA times the gauge fixing function, Fa. Now, I can write one of the dA's as the variation of B divided by lambda. And then this D also has the variation of B divided by lambda. So all in all, the variation of the Gauss plus gauge fixing term, it's all proportional to the variation of, well, so remember that remember that the variation of this thing was equal to 0. So I can put together as the whole variation of this product. So let's verify here. So if I consider B times F, so it's variation of B times F plus variation of B times variation of F, which is the ghost term. Then from the second term, I have variation of B times gamma AB dB over 2, so that's this term. And then B times variation of this thing, which cancels B times variation of FA. And then finally I have variation of B times this term, which was here. So this form is valid even more generally, and notice that it kind of trivializes the BRST invariance on the quantum action. The point is that now I've written a classical action that is by definition BRST invariant, since BRST invariant is a residual gauge symmetry, plus one variation of something, but then two variations, so variation squared is equal to 0. So this thing can be anything, and it will always be equal to 0. So I can even call this thing I can call it the gauge fixing fermion, call it psi, and here is B times F plus gamma AB over 2D, but perhaps it can be even more generally something else. So I can write some quantum action as classical action plus write it as an anticommutator, which means the variation of B divided by lambda of so QB with psi being the generalization of this thing. So if I write it like this, then it is trivially invariant, and this is a more general quantum action. So this BRST formalism, I've shown it here, but we will, as for the moment, it looks kind of abstract, but we'll see that it's actually very useful, that we can calculate relations between various correlators that sort of replaces the word identities that we had from the gauge invariant formalism. All right, I think this is everything I wanted to tell you today. Do you have any questions? Can somebody check that you can still hear me?
Yes.
All right, so that means no questions. So that's it, and I'll see you next Tuesday at 10. All right, bye.